I'll go over the notes real quick, and I have a separate video for the very last example on 6.2 to show you how to do, how to graph a binomial distribution in a calculator. That's a fairly long tutorial of its own, so there'll be a separate video for that. But let me work you through the first four examples here real quick. Hopefully we can get you to understand the concept, and then you'll be good to go. Okay, so we want to talk about binomial distributions today. So construct and interpret binomial distributions. First of all, more generically, we just want to talk about probability distributions in general, and then more specifically, ones that are binomial in nature, and then we'll introduce you to the concept of symmetric distributions or skewed distributions. Okay. And so let's look at this first. First of all, we're going to talk about probability. If we're going to talk about a probability distribution, then we should talk about what is probability. So probability is usually defined like this. The probability of an event A is the number of outcomes in the event A divided by total number of outcomes. All right. So here is an example of probability that says if we have names for this that's really not part of our Algebra 2 course, but this would be called my sample space, and say that contains all possible outcomes. There's 8 possible outcomes, and if event A is these 3 possible outcomes, then the probability of event A occurring is 3 out of the total 8. Okay, so that's what this is saying. That's maybe not the clearest example for you. Maybe you're looking at that going, not sure what you're getting at. So think about this. If you toss a coin, there's 2 options. You can get a head or you can get a tail. Okay, so if you toss a coin, okay, those are my 2 options, head or tail. And so that tells me that the total number of outcomes for tossing a coin is 2. All right. And then if we define event A as I toss a head, okay, and we say how many ways can I toss a head when I toss a coin? And there's only one way. I toss the coin and it lands with the heads up. So you go, oh, this number of outcomes here is 1. Okay, so if we want to just stick to this basic definition of probability up here, then we say if event A is tossing a head, so the probability of event A, or which is the same as probability of tossing a head, would be equals to, again using this understanding, the number of outcomes in event A, which would be 1, and then the total number of outcomes, which we said over here, is 2. Okay, so now I know most students understand that there's a half chance that when I toss a coin I get a head, but this is a more formal understanding of what probability is. Okay, and so what we did in the previous section, we were talking about counting combinations. Well, if you do serious probability calculations, you have to count combinations. And you'll see it comes in a little bit handy in our first example here, but it's a basic understanding of how we're going to view probability. Okay, so hopefully that's clear for you. And then we want to talk about a different concept, which is a random variable. It's a different concept. Now, a random variable is a variable whose value is determined by the outcomes of a random event. All right. So in this case, we had tossing a coin. I had 2 options. I can either get a head or a tail. Okay, that's the 2 values that can happen when I define my random variable as, the outcomes from my random variable could be a head or a tail. It's a random variable because I'm tossing a coin, and that process is, we consider the process of tossing a coin random. Okay, in other words, it's equally likely that I get a head or a tail. All right. Here they mention rolling a 6-sided die. Okay, and we also consider that a random process or a random event, tossing a die and then getting a number or an outcome. Okay, and they said let's define the random variable x as the number showing on the die when I roll a die. Okay, and so there are 6 outcomes. I can get a 1 or a 2 or a 3 all the way up to 6. All right, and those are the values that the random variable can take on. And again, it's a random variable because rolling a die, we're calling a random process because we don't know what the outcome will be of rolling a die, and in this case for a die, each outcome is equally likely. Okay, so that's what we call a random variable. Basically, a random variable is a variable whose value is determined by the outcomes of a random event. Tossing a coin is a random event. Rolling a die is a random event. There's many other random events we can come up with. All right. So it says for every random variable, a probability distribution can be defined. Okay. So in other words, I can list all the outcomes and all the probabilities of each outcome in a nice clear way, a table or a graph, and then I know everything about that random event. Right? I know everything about the probabilities of that random event. So probability distribution is defined here. It says it's a function that gives the probability of each type of possible value of a random variable. So we were just talking about rolling a die. So if we say let x be the number showing after you roll a die, then x can be 1, or x can be 2, or 3, or 4, or 5, or 6. Okay? And then we say it gives the probability of each value. Okay, so what's the probability if I roll a die of getting a 1? That's the question. Now you know, if you look down here, I try to define it for you. The probability of getting a 1 is the number of ways of getting a 1 when I roll a die. Well, there's only one way. I roll the die and the number 1 shows face up. Okay, so 1, and then what's the total number of ways of getting any number? Right, total number of ways of getting any number. So as we had up here, total number of outcomes, right? The total number of ways of getting any number, and that's 6. Now, okay, I think that's intuitive for most of you. You've been around probability a little bit, hopefully, and so that's fine. So I get there's a 1/6 chance of getting a 1, but then there's the same chance of getting a 2 because there's 1 2 on the die, and there's one way that you can get it 2, and there's 6 possible outcomes on the die. So 2 has the same probability as 1, and so does 3, and so does 4, 5, and 6. Okay, so this is a nice little probability distribution. So please remember, we call this whole thing the probability distribution. Okay, you give all the possible outcomes and the probability of each outcome. That's probability distribution. And it has one big property. Probability must be a number between 0 and 1. So each of these must be a number between 0 and 1, and they are. And when you sum them all up, 1/6 plus 1/6, 6 times, you must get 1. All right? That's the other requirement of a probability distribution. Each outcome must be between 0 and 1 probability, and the sum of all of the outcomes probabilities must be 1. All right? So, it's a lot of definition, a lot of talking. Let's do an example, hopefully, and so you can see how this works. Right? So this is a little bit more tricky, actually. It says, let x be a random variable that represents the number of heads when 4 coins are tossed. Let x be a random variable, okay, that represents the number of heads when 4 coins are tossed. Okay, so x is the number of heads when 4 coins are tossed. Okay, so a little bit and write out the options. Right, so what are the options? The number of heads when 4 coins are tossed. So if I toss 4 coins, let's make 4 slots here. Okay, think about it. what are the number of heads I can have? Well, I can have no heads, that's tail, 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 on the 4 different coin tosses. Okay, or I could have, again with 4 slots, I could have 1 head, a tail, 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 all right? And then that's one option. So if we want to think about it this way, for making a table, all right, let's try and think about it that way. If I make a table and I write X over here, and remember X is the number of heads when 4 coins are tossed. We have some options. We're busy writing down the options right now. So we just said this is an option where I have 0 heads. Okay, so that's one option, 0 heads. This is an option where I have 1 head. And I think if you just keep going with this, you can see the other options emerge fairly quickly. What if I have 4 slots here, 4 coin tosses, and I have a head, and then a tail and tail. Okay, so this is an option where I have 1 head. This is an option where I have 2 heads. That's another possible outcome, 2 heads. And you can continue like that until you get 3 heads. And finally, you would end up, if I toss 4 coins, I would have head, 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 head. Okay, so 4 heads. All right, the difference between this probability distribution and the die probability distribution is that not each outcome is not equally likely. Okay, so getting 0 heads is not doesn't happen in the same number of ways as getting 1 head. So let me try and elaborate there a little bit. If I erase this real quick, let's think about this. This is one way of getting 1 head. But there's another way I can toss 4 coins and only get 1 head. What if on the first toss I get a tail and then a head and then a tail and then a tail? That's still only 1 head, but it's another way of achieving 1 head. And then I can do yet another arrangement, tail, tail, head, tail. Okay, still just 1 head, but that's the third way. And then I can do tail, 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 head. Okay, 4 coin tosses, still only 1 head, but a different way of getting 1 head. It's the head on the 4th coin toss. So actually this shows me those are all the number of ways that I can just toss 1 head. Okay, and that's 4. All right. So here there was only 1 way of getting a 1, 1 way of getting a 2, 1 way of getting a 3. But now we have a different situation. So making our table is a little bit different from rolling a die. I think what we should probably do then is see if I can erase this stuff pretty quickly here. I think what we should probably do then is say, let's count the number of ways to get each outcome. Okay, so we're counting now combinations, basically, of how to get each outcome. Now I listed all 4 for you. So the only way that you can get 0 heads is 1 way. They're all tails. There's no other way to achieve that. But I just listed for you the 4 ways that I can get 1 head. So that would be 4. Okay? And then how many ways can I get 2 heads? That's the other question. Now, it becomes inefficient to list all the ways here. You can keep doing this, but it's a lot of work. And especially when you're working with larger number of coins or possible outcomes in a random process, it becomes quite difficult to list everything. So better to think about it in terms of combinations. So what you can think about it this way is we have 4 coins, okay? 4 coins, coin 1, coin 2, coin 3, coin 4, and I choose none of them to have a head. So 4 choose 0, turns out that's 1, okay? Which is what we got here. And then if you check it out again, if I have 4 coins, okay, and one of them is a head, so like head, tail, 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 all right, then I have 4 choose 1. 4 coin tosses, choose one of the coin tosses to have a head. And if you work that number out, it's 4. All right? So it seems like that's a better way to proceed, thinking about counting combinations rather than listing out all the combinations. That would take forever, okay? Especially if your random process has many outcomes. So that's 4. And then, oh, how about 4, choose 2? We're here, 2 heads, okay? 4 coin tosses, choose 2 of them to have a head. And if you do that, you get 6. Now, we did give you the strategy how to do this last class. How do I come up with 6? Well, we said do Pascal's triangle. Okay, if you don't want to use your calculator, you can quickly do this kind of thing and just go, oh, this is the first row, second row, third row, fourth row, and I'm doing combinations of 4 coins. So I want to do this. This is 4, choose 0, etc. Okay, so we're not 4, choose 2 is 6, so we know that works. And then we know what the next one would be. 4, choose 3, 4 coins, choose 3 heads. That would be 4. Okay, and then 4, choose 4, that would be 1. So I'd have 4 here and 1 here. That's the number of ways that I can get those outcomes. Okay, and now we need to convert that into a probability. So a probability distribution has the outcomes themselves, okay, and then the probability of each outcome. So all we've done so far is these are the outcomes themselves, and we need to go and list the probability of each outcome. Now we needed to calculate the number of ways to get each outcome to come up with the probability. Okay, so remember we said probability is number of outcomes in an event over the total number of outcomes. Right? So that brings us to another. So we have another question. So the probability of getting each outcome. Well, probability of getting 0 is there's one way to get 0, but what is the total number of outcomes that I can have? If I toss 4 coins and I get 0 heads, 1 head, 2 heads, 3 heads, 4 heads, what's the total number of outcomes I can have? Well, this is the total number of outcomes. We've listed every single possibility for outcomes. And if you add that all up, you get 16. Okay, 16 outcomes. You can think about that another way and say there's 2 possible outcomes on the first coin toss, a head or a tail. And there's 2 possible outcomes on the second coin toss. Let's say this is coin 1. Okay, coin 1, coin 2, that's head or tail. And then coin 3, and there's another 2 possible outcomes, head or tail. And on coin 4, there's another 2 possible outcomes, head or tail. Okay, and that's also 16. So either way you want to do that, you can come up with the total number of outcomes is 16. So we've done it. Now we have the number of outcomes for each event divided by the total number of outcomes. Okay, so now we have basically our probability distribution. So let me clean it up a little bit here. I've got all kinds of scribbles going on here as I was trying to explain this to you, but yeah, that's our, and I erased too much there. That's our probability distribution, okay? Now, there's other ways of representing the probability distribution. This is one, using a table, okay? And the question said make a table and a histogram. Now, a histogram is a very specific type of data display. It's very, very powerful, but it's a very specific type of data display. So let me move this over to the side here, and then I'll show you how to make a histogram. Making a histogram by hand, kind of annoying, to be honest, but it's a very, very powerful display. If you were going to do this, professionally or do it a lot, you'd use software like RStudio or Calculator or something. We'll do a probability distribution on our calculator later, but even then it's quite tedious. In any case, a histogram has 2 axes, vertical, horizontal axis, okay? And usually what you put on the bottom of the histogram is the outcomes of the probability distribution. So in our case, it will be the number of heads or the values that X can take on. In our case, there were 5. Can be 0 heads, 1 head, 2 heads, 3 heads, or 4 heads. Okay, 4 heads. In any case, and then probability of each outcome, probability P of X, would go on the vertical axis. And I did not simplify this because it's actually easier to draw if it's all in terms of 1/16. Okay, now that takes a bit of thinking sometimes, but in this case it's easier to draw if you didn't actually reduce it all to eighths and sixteenths and things like that. Just leave it all with a common denominator. It's easier to graph that way. And you'll see why in a second. So if I do, I'm just going to split this. My biggest bar should be 6 out of 16. So I'm just going to keep a consistent scale here on the vertical axis and go, this, we'll call this 1 out of 16, 2 out of 16, 3 out of 16, 4 out of 16, and so on. 5 and 6 out of 16. So that's my biggest bar, 6 out of 16. So I can easily draw this now. I just say for probability of getting a 0 is 1 out of 16. And so I can make my bar here. Okay. Now, please, a histogram, it's not a bar graph. A histogram is different. A histogram, the bars have to touch each other to show that there's nothing in between the specific values on the horizontal axis. So if I make my next bar 4 over 16, it has to touch this bar. Okay, it's not like a bar graph. There's no value in between 0 and 1. When I toss 4 coins, I either get 0 heads or 1 head. I can't get like a half head. That's not possible. There's nothing in between these two. So the bars have to touch each other. Okay, we call this a discrete probability distribution if you take AP statistics. Okay, and so for 2, the probability is 6 out of 16. For 3, the probability again goes back to 4 out of 16. And then for 4, getting 4 heads, there's only one way that can happen, so 1 out of 16 outcomes. And that's my probability distribution as a histogram. So this thing is called a histogram. It's not a bar graph. Okay, it shows frequency, and the bars must touch. It's a very different kind of display from a bar graph. All right. So there's the histogram, and this is the table showing the probability distribution for that process. Okay. I hope that was clear for you guys. All right, so, and then we can answer some questions based on this. It says, use probability distribution in example 1 to answer the following questions. What's the most likely outcome of tossing 4 coins? Okay, what happens most? What's the most likely? What has the highest probability? Most likely means highest probability, and that would be obviously 2, okay? So you can write it like this, and you can say the probability of 2 heads is 6 out of 16, and you can reduce that if you really want to 3 over 8. That has the highest probability, so it's the most likely outcome when I'm tossing 4 coins. All right? And then what's the probability of at least 2 heads? At least 2 heads. Well, at least 2 heads means 2 heads, or 3 heads, or 4 heads. Okay, so these are my outcomes that are at least 2 heads. So we say, oh, it's the probability of 2 heads, or, but remember we said last class, or means plus in mathematics, the probability of 3 heads, or the probability of 4 heads. Okay. And if you do that math, you just fill in the numbers, you get 6 over 16 plus 4 over 16 plus 1 over 16. And you should get 11 over 16, which can't reduce. And just remember, check yourself always. A probability question, this is a probability question, can never have an answer that's bigger than 1. It must be between 0 and 1. So you know you didn't make an obvious mistake at this point. All right? Okay. Let's move on. Let's talk about a more specific probability distribution. That's called a binomial distribution. So a binomial distribution is still a probability distribution like this, example 1, same thing, but it's more specific. It has qualities that are required in order for something to be called a binomial distribution. So binomial distribution, it's very useful. We use this for a lot of different scenarios in statistics to calculate probability, because you can use this to match real-world scenarios, of course, like all mathematics. And so binomial distribution, okay, shows the probabilities of the outcomes of a binomial experiment. Well, okay, well, what's a binomial experiment? So a binomial experiment is defined down here. Okay, it meets the following conditions. Well, what are the conditions for a binomial experiment? There are n trials that you know in advance. Okay, so something is happening a specified number of times in advance. Okay, And then each trial has only two possible outcomes, success or failure. Now that's seems simple, but not so simple. So you can have success or failure, but I have to explain that a little bit. So I wrote that most of this stuff's not in your textbook, unfortunately, but I wrote down some ideas here for you to know. So success and failure in a binomial experiment is not literally just meaning head or tail. That's not what it means. Okay, it means I define one outcome in my random process as a success and the other possibilities as a failure. In other words, here's a good example. It says if you want to count the number of students in a high school that are exactly 6 feet tall, okay, you would say, all right, I define finding a student who's exactly 6 feet tall as success, and then finding a student that's any other height a failure. So here are examples of failures, not that being a specific height makes you a failure, but in terms of this probability distribution, we would consider those outcomes, these ones right here, ones that we are not considering a success, so we call that failure. Okay? So there's many options for failure and one for success, right? Or there could be one for success and one for failure, but it doesn't have to be binary like that. There can be more options besides just head or tail or something like that. Okay, so that's what we call success and failure. You must be able to say what do we call success and what do we call failure for the experiment or for the binomial setting. It's another way we call it binomial setting. Okay, and then the probability of success is the same for each trial. So if it's a coin toss and you're saying what's the chance of getting ahead, probability on a coin toss of getting ahead is always the same. Okay, that's what we mean by probability of success is the same on each trial. All right, so that's this. And then if this probability is denoted by, the probability of success we call P, small letter p. And then it means the probability of failure of not getting a success would be 1 minus p. Okay, because all the options together must make 1, right? So p plus 1 minus p is 1. That's all the possibilities, right? And then for a binomial experiment, the probability of exactly k successes in n trials is this. Please don't memorize this. We'll give you the formula. There's no need to memorize this. It's more important that you understand what the formula is saying. Okay? And it's actually really, really remarkable. All right? But before I move on to looking at the formula, just one other thing I want to address with you, and that's this big word here in mathematics and probability. It's called independence. Okay, what does it mean for a trial to be independent? So a trial just means it's one repetition of the random process. Okay, so tossing a coin would be one trial of the random process, which is tossing a coin. Okay, that's what we mean by trials. But independent means that one trial doesn't impact the outcome. The outcome of one trial doesn't influence or impact the outcome of another trial. So coin tossing is an excellent example of this. When I toss a coin, I get ahead. The fact that I got ahead on the first coin toss does not affect the outcome of my next coin toss. Okay? So coin tossing is an independent process. Those trials, each coin toss would be called independent of each other. They don't affect each other. Okay, so before you can start using this formula and defining things and calling things binomial, before I can use this, all of these conditions have to be met. Okay, and again, if you take a higher level statistics class, then we'll make you actually write all those conditions out every time. Okay, so assuming that the conditions are met, then you can use this kind of a formula. This is the binomial probability formula. Okay. And k successes. So let's say, let's jump in and do an example. Let's do example 3, and then hopefully this formula will become clearer to you. Okay. So example 3 says a health clinic knows that 80% of their patients visited the clinic in the last month. The clinic will call 5 randomly selected patients and ask if they have visited the clinic in the last month. Okay. Draw a histogram of the binomial distribution for the survey. All right. So we could make a table like we did last time. That's a bit tricky. It's a bit more difficult. So similar but not the same. So let's think about this in terms of trying to use the probability formula here. Okay, the binomial probability formula. So we have some components. We need the number of trials in advance, n. Okay, can we identify the number of trials here? The clinic will call 5 randomly selected patients. Okay, so calling 5 randomly selected patients, that seems to me like n, the number of trials, the number of phone calls I'm making will be 5. Okay, and then we need k, the number of successes. Okay, k is the number of successes. So what are the options for number of successes? Okay, and what is success? So we will ask if they visited the clinic in the last month. All right, and we know that this says probability 80% of visiting the clinic. So we will call success is if someone has visited the clinic. All right, that's a success. Okay, and then we're saying, according to the hospital records, the probability of success is 80% or 0.8. Okay, that's the chance that you visited the clinic in the last month. But now they're going to repeat the process and just call 5 randomly selected people and see what happens. Okay, and so we have to say what are the options. So I call 5 people and none of them say they visited the clinic. Okay, that's one option. So you can say no one visited the clinic. That's one option. Okay, that would be 0 successes. After 5 calls, no one visited the clinic. All right, and then how about 1 person visited the clinic? That would be 1 success. And then so on. 2 people, okay, visited the clinic, which would be 2 successes, and so on. Okay, so what are all the options? I can go up to 5 people visited the clinic. Okay, and that would be 5 successes at that point. Okay, and so this, we can use this to calculate probabilities. All right, so here's what we're doing. We're saying, look at this option and say, what is the probability of 0 successes? I call 5 people, no one says they visited the clinic. Okay, now we can use our probability formula from here to do that. So plug stuff into the formula, we just do this. We get probability of 0 successes is 5 trials, that's my n, okay, that's my n, and 5 trials choose 0 successes times 0.8 to the 0 times 0.2 to the 5. Okay, so probability of success is p, this is p, k successes, in our case k here is 0, and then 1 minus p would be 0.2, okay, this is 1 minus p, and then n minus k is 5 trials minus 0 successes, in our case, which is 5. All right, so that's the formula, how you fill it out, and then you can calculate probability here. So you can do this on your calculator. Let me switch to my calculator real quick. And remember, you go, there's 2 ways you can do this. I'll just do alpha window, and then you can go to number 8, okay, and we want to say 5 choose 0, 5 choose 0, and then multiply it by 0.8 to the 0th power, and then we want to go to 0.2 to the 5th power. Okay? And you do that and you get this number. This means 0.00032. That's what that means. Okay? So 0.00032. And then we do probability of one success, and we get, again, I'll go faster, 5 choose 1, 0.8 to the 1, 0.2 to the 4. Okay? So one success, 4 failures. Probability of success, probability of failure. And if you do that, now it's easy. Once you've done the first one on your calculator, you can just go up, enter, bring this down, and then just change the numbers. Okay? So if you change the numbers, you get 5 choose 1, and then 0.8 to probability of success to the number of successes, probability of failure to the number of failures. Enter, and then you get another number, 0.0064. Okay? Then you get 0.0064, and so on. So I'll just fill this in. I've already done all the work here on my end. You can do this on your own to practice as well, but you end up getting this 0.0512 and so on. Probability of 3 successes, 4 successes, and 5 successes. Okay, and I'm not going to fill in the formula the whole time. You get the idea. I'll let you do that, but you get 0.2048, 0.4096, and then 0.3277. All right, and so here are my probabilities that I want to make a graph out of. All right, and so again, histogram we did before, same idea. The histogram is just the vertical axis, horizontal axis. On the bottom, you put the number, the values that the variable can take on. In this case, the number of successes here, and then you just put probability of each outcome. So this is x, this is probability of x, probability of each outcome. And we go from, our biggest one is 0.4096. So we can do something like, maybe, I don't know, 0.05, 0.1, 0.15, 0.2. Let's just make some check marks here. I'll write the numbers there. I did 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, and 0.4. Okay? And if you make the bars now, 0 successes is, that bar should be almost nothing. Okay? 0.0064 is still way, way less than this for 1. So check here, check here. 0.05, okay, that's just a little bit above 0.05 there. And then 0.2048 is for 3 successes. 2048, just a little bit above this bar right here. All right. Oh, that bar is way thick, but okay, whatever. And then 0.4096 would be all the way up here. 0.4096 just above 4. 0.4 probability, and then 0.3277, and you're maybe over here. Okay, and that would be that. And then we can use this again to answer questions. So what's the most likely outcome? It's just the highest bar. Okay, it's the highest probability of the highest bar, and you say the probability of 4 successes. Okay, which is 0.4096. It's this one, okay, highest bar. And then at most 3 people means probability of 0, probability of 1, probability of 2, or probability of 3. Those are all the options, okay? And if you add all those numbers up, you get 0.0032. Oh, sorry, there's another 0 in there. 0.00032 plus 0.0064 plus 0.0512 plus 0.2048. And then you get 0.2 0.2672. Okay, that's probability that most people visit a clinic. All right, guys, and then the next video you can watch has the explanation for example 5 and skewed and symmetric.